In last video, we've learned that there will be a section in a uniform circular motion, and then in this video, we'll go to learn how to derive the formula of centripetal acceleration. So first of all, I call it the centripetal. What does the centripetal mean? Central it means center, okay? Petal means towards. So it means something it towards the center of the circle. And then when I derive it, and then we'll see why the direction of the acceleration is towards the center. So first of all, let me draw a circle here, and then let's say this is time 0, okay, and then this is after the time delta t, okay. And in a uniform circular motion, the speed is a constant. So that means the magnitude of v1 and v2 are equal. Okay. The only difference is the direction of the motion, the direction of the velocity v1 and v2, and we call the speed to be v. Okay, and then let's say how we can derive the centripetal acceleration. So from the formula, from the definition of the acceleration, and we know that acceleration is change in velocity divided by change in time, or in word, is rate of change in velocity. So when you how can we find the change in velocity of from the time 0 to time delta t? So I just move these two vectors v1 and v2 to the right hand side, and then to make the tails join together. So we know that the change in the velocity should be final velocity, that is v2, minus the initial velocity, that is the v1. So how can we get the delta v on the diagram? Okay, if you are very familiar with the vector addition or subtraction, and then you can see it easily. But if you can't, maybe just say v1 plus delta v equal to v2. Okay, so v1 plus a vector equal to v2, and then so the delta v should be the vector joining the tip of the v1 to the tip of the v2. So this is a change in the velocity. Okay. Oh, but the problem is now, how can we get the magnitude of the change in velocity on this diagram? So actually, by mathematics, I'll prove it soon, and this angle is also the delta theta, as stated here. So let me show you why this angle is delta theta. So let me extend the line of v2, okay? So the angle here is also the angle here. You can see the angle between the v1 and v2 is the angle here. And then we know that the velocity is tangent to the circle. That means this one is a right angle, and this one is also a right angle. So let me assume this angle to be phi, okay, phi. So I think you can now see that this is a quadrilateral. So the angle sum of the quadrilateral is the angle sum of the all induced angle of a quadrilateral is 360 degree. Okay, 360 degree. And then therefore the angle phi is actually 180 degree minus the delta theta. Okay, and then we use the angle on the same straight line. This angle plus this angle should equal to 180. Therefore this angle should be also delta theta. Okay, okay. And then how, okay, if we know that this angle is delta theta, how can we get the magnitude of delta V in in this diagram? So we need to assume that the angle is very small, such that this triangle is a very thin triangle. Okay, something look like this one. V2, V1, and delta V. And then we need to use a formula in mathematics. In a sector, okay, in a sector, the arc length is equal to r times the angle theta in radian. So how about here? We know that this is a straight line. This is not a arc length, but if the angle is very small, the magnitude of delta V will be very close to the arc length of this sector. So we can say that the delta theta will be roughly equal to, okay, these two have the same magnitude, V1 and V2 have the same magnitude, will be equal to V times delta theta. Because in this sector, the radius is V1 or V2, that is V, the angle is delta theta, okay? So the arc length is roughly equal to V times delta theta. That is the change in velocity. So, and then we substitute the change in velocity in the formula of the acceleration. Okay, V times delta theta and then divide by delta t. So for delta theta divided by delta t, we know that that is the definition of omega, angular speed. So we have this formula, A equal to V times omega. But actually, this form is not the form that we always use. And then let me remind you this formula. Okay, so we can substitute the V inside the formula, and then you can get R omega squared. Or you can make the omega to be a subject of the formula and then substitute in. Okay, and then you can take some time to try to do it, and then you can get V squared for R. So this is the formula of the centripetal acceleration. And then in next lesson, and then we're going to have a look how can we use this formula to find the force or solve the questions. And then, okay, oh, something left, okay, is the direction of the acceleration. So why is it centripetal? So if you look at the change in the velocity here, okay, so it's roughly towards the center of the circle. I can't prove it in another easier way for you unless you have learned the calculus. So and then it's better for you to just accept the result of this proof, and then this derivation is not likely to be appear in the public exam. So what you need to do is to remember this formula and notice that the acceleration is always towards the center of the circle. So let me draw a circle again. Oh. So let me draw a circle here. Okay. So when an object is at this position, okay, let's say an object is moving in a circular motion, uniform circular motion, and clockwisely, okay. So the velocity is always tangent to the circle, and the acceleration of this motion is always towards the center. And then, okay, you may ask, this is right angle to each other. So what happens? What happens if there is no acceleration in the circle motion? If there's no acceleration in the circle motion, and then you can just use the Newton's first law, and then the object will move in a straight line. Okay. So I've shown you the direction of the velocity and the direction of acceleration in different positions. Okay. I hope you can understand the concept of the centripetal acceleration. Okay. It's always towards the center. Oh, but I'm not drawing on scale. Okay. So in next session we're going to do some calculations. Okay. See you.